The universe is an immense and complex entity that includes all planets, stars, galaxies, and the entirety of space and time, along with all the energy and matter within it. And today, we'll take a look at how protons, the building blocks of matter, formed from the void, nothingness. Scientists estimate that the universe is about 13.8 billion years old, based on observations of the cosmic microwave background radiation. This radiation is a remnant from the early universe and helps us understand its age. The universe is not static, it is constantly expanding. This idea comes from the Big Bang theory, which suggests that the universe began as a singular point and has been expanding ever since. This ongoing expansion challenges our understanding of space and infinity, stretching the limits of our knowledge about the cosmos. Adding to this complexity is the presence of dark matter and dark energy, which make up about 95% of the universe. These mysterious forces influence the universe's structure and future evolution. Cosmology, the scientific study of the universe's origin, structure, and dynamics, aims to uncover the mysteries of the cosmos. Scientists use various advanced methods and technologies to study the early universe, with the cosmic microwave background radiation playing a crucial role. This faint glow, often called the afterglow of the Big Bang, fills the universe and provides a snapshot of what it looked like around 380,000 years after its formation. At this point, the universe had cooled enough for particles to form atoms and for light to travel freely. By examining the small temperature variations in the CMB, researchers can learn about the distribution of matter and energy in the early universe, helping them understand its structure and evolution. But it's not just about what we see. Computer simulations also play a vital role. These simulations, based on the laws of physics, allow scientists to recreate the conditions of the early universe on a massive scale. They help us understand everything from the formation of the first atoms to how galaxies clustered together to form the complex web we see today. By combining observations with theoretical frameworks, scientists can piece together the universe's history. This approach opens doors to new discoveries about where we come from and where we're headed. Within the universe, 4 fundamental forces shape everything we see. Gravity, perhaps the most familiar, is also the weakest. It governs the attraction between objects with mass, from the sway of an apple falling to Earth to the graceful orbits of planets around stars, sculpting the universe's grand structure. Moving on, the electromagnetic force is responsible for how charged particles interact with each other. It's what allows atoms to bond together to form molecules and creates the light we see. Plus, it's the force behind electricity and magnetism, which are essential for much of today's technology. Then there's the strong nuclear force, which holds the nucleus of an atom together. It's incredibly powerful, overcoming the electromagnetic repulsion between positively charged protons to bind the particles in the nucleus tightly. However, it only operates within the nucleus itself, making it the strongest force but with the shortest range. Lastly, there's the weak nuclear force. This force is responsible for processes like radioactive decay and nuclear reactions that power stars. It's vital for synthesizing elements and enabling the sun to shine, ultimately supporting life on Earth. Together, these forces create the intricate tapestry of the universe. From the tiniest particles to the vast structures of space, their interplay shapes everything we observe, offering insight into the fundamental principles governing our reality. Particle physics, a branch of science, dives into the smallest building blocks of the universe and the forces that control their interactions. It explores particles like quarks, which make up protons and neutrons, as well as leptons like electrons and neutrinos alongside bosons, the carrier particles that mediate the 4 fundamental forces of nature. If you're still watching, hit the like button and turn on notifications for more documentaries. Thank you so much. Particle physics delves into profound questions about mass, the structure of space and time, and how the forces shaping the universe come together. At its core lies the Standard Model, a theory developed during the latter part of the 20th century. This model outlines how electromagnetic, weak and strong nuclear interactions work, explaining many experimental results and the existence of various particles. However, it doesn't account for gravity, as described by the general theory of relativity, presenting a major challenge for theoretical physics. Experiments in particle physics often involve accelerators that propel particles to high energies, simulating conditions akin to those just after the Big Bang. When these particles collide, detectors capture the aftermath, allowing scientists to study their properties and the forces involved. Facilities like the Large Hadron Collider, LHC, at CERN have been crucial for groundbreaking discoveries such as the Higgs boson, which explains how particles acquire mass. Yet despite these successes, many questions remain unanswered. Scientists continue to explore phenomena beyond the standard model like dark matter, supersymmetry, and the grand unification of forces in their pursuit of deeper understanding. Particle physics is a pathway to understanding the fundamental rules that govern our universe, unveiling its intricate design at its most basic level. It provides a foundational framework for grasping the complexities of the cosmos, not only revealing its composition, but also illuminating how it operates at its core. At the center of this exploration lies the standard model of particle physics, a comprehensive theory that organizes all known fundamental particles, quarks, leptons, and bosons, and explains 3 of the 4 fundamental forces, leaving out gravity. Through this model, scientists can decipher a multitude of phenomena ranging from the behavior of atoms to the processes fueling stars like the Sun. One of particle physics's greatest contributions to our cosmic understanding is its explanation of mass's origins. The discovery of the Higgs boson, famously dubbed the God particle, in 2012, at the Large Hadron Collider revealed its crucial role in giving mass to other particles. Without this mechanism, the universe would be vastly different, unable to form the building blocks of matter like atoms and molecules. Particle physics ventures into the universe's early stages, offering insights into moments shortly after the Big Bang, where unimaginable temperatures and energies prevailed, causing the 4 fundamental forces to merge. By studying these extreme conditions, particle physicists delve into symmetry breaking, a phenomenon that may clarify how these forces developed their distinct properties as the universe cooled and expanded. Despite its impressive success, the standard model isn't all-encompassing. It doesn't incorporate gravity, which is explained by general relativity, nor does it account for dark matter and dark energy, together constituting about 95% of the universe. Therefore, particle physics isn't just a tale of achievements, but also a narrative of mysteries yet to be unraveled. It fuels the quest for a more comprehensive theory of everything, aiming to elucidate not only the realm of the infinitesimally small, but also the vast complexity of the cosmos as a whole. The Big Bang Theory. The Big Bang Theory stands as the leading model in cosmology, outlining the universe's early stages and its ongoing expansion. According to this theory, the universe sprang forth from an incredibly dense and hot point roughly 13.8 billion years ago. From this starting point, the universe expanded and cooled, leading to the formation of basic particles and atoms. Over time, gravity pulled matter together, forming stars, galaxies, and larger cosmic structures. One key piece of evidence supporting this theory is the cosmic microwave background radiation, a faint glow lingering from the universe's infancy around 380,000 years post-Big Bang. Additionally, the observation of galaxies moving away from us, indicated by their redshift, further solidifies the Big Bang Theory by showcasing the universe's ongoing expansion. Contrary to its name, the Big Bang wasn't an explosion within space, rather, it marked the rapid expansion of space itself. This realization deepened our understanding of the universe's dynamics, highlighting its destiny linked to the density of matter and energy it contains. While the theory doesn't address what existed before the singularity or what triggered the expansion, it provides a cohesive framework for understanding the universe's journey from a hot, dense state to the complex cosmos we observe today. Its elegance lies in its ability to unify diverse astronomical observations into a coherent narrative of cosmic evolution. The Big Bang initiated the universe's expansion with a rapid inflation phase, a pivotal concept linking the singularity to the structured cosmos we observe today. Unlike an explosion within pre-existing space, the Big Bang marked the simultaneous birth and expansion of space itself. Within the first fleeting moments, the universe exponentially ballooned from a point of near infinite density and temperature to a significantly larger scale. This rapid inflation set the stage for the universe's large-scale structure, smoothing out initial irregularities and leaving behind a remarkably uniform cosmos. As the universe expanded and cooled, energy transformed into various subatomic particles, following the processes outlined by the standard model of particle physics. These particles eventually combined to form hydrogen and helium atoms in a process called nucleosynthesis. Following inflation, the universe's expansion persisted at a slower rate, driven by both the initial momentum and the continued repulsive force of dark energy, an enigmatic force accelerating. Cosmic expansion. Gravity then stepped in, playing a crucial role in shaping galaxies and larger cosmic structures after the inflationary period. The ongoing interplay between cosmic expansion and gravitational forces shapes the universe's structure and evolution. As galaxies move away from each other in the vast cosmic expanse, their redshifted light provides tangible evidence of this continuous expansion, a direct consequence of the Big Bang. This underscores the universe's dynamic and evolving nature, fundamental to modern cosmology. Crucially supporting the Big Bang theory is the discovery of the cosmic microwave background radiation, CMB. Accidentally detected in 1965 by Arno Penzias and Robert Wilson, the CMB is a faint radiation permeating the universe, serving as a relic from its early hot and dense phase. While uniform in all directions, subtle fluctuations within the CMB mirror the ancient distribution of matter in the universe. This radiation offers a direct glimpse into the universe's state around 380,000 years post-Big Bang, when it had cooled sufficiently for electrons and protons to merge into neutral atoms, allowing light to travel freely. Further evidence supporting the Big Bang theory stems from observing the universe's expansion. In 1929, Edwin Hubble noted that distant galaxies were receding from us, with their speed proportional to their distance. This phenomenon, known as redshift, aligns with a universe expanding from a hot, dense state, as predicted by the Big Bang theory. Additionally, the relative abundance of light elements lends further support. The theory suggests that shortly after the Big Bang, nuclear fusion processes formed hydrogen, helium, and trace amounts of lithium. Observations of these light elements in the oldest stars and interstellar space align closely with the predictions of Big Bang nucleosynthesis. These pieces of evidence, the cosmic microwave background radiation, the expanding universe observed through galaxy redshift, and the abundance of light elements, stand as foundational pillars bolstering the Big Bang theory. Together, they offer a coherent and comprehensive narrative explaining the universe's origins, its 8 billion year evolution, and its present-day structure and composition. In the aftermath of the Big Bang, the universe was unimaginably hot and dense, unlike anything observable today. At this initial stage, temperatures soared to levels where matter and antimatter particles were spontaneously created and annihilated in equal measure. This intensely energetic phase filled the universe with a quark-gluon plasma, a unique state where quarks, the building blocks of protons and neutrons and gluons, carriers of the strong force-binding quarks, roamed freely, not yet confined within particles. As the universe rapidly expanded, it cooled, passing through various critical temperature thresholds that triggered significant transformations in its makeup. Around 1 microsecond post-Big Bang, the cooling allowed quarks and gluons to amalgamate into protons and neutrons. A few minutes later, as the universe continued to cool, protons and neutrons began combining to form simple atomic nuclei in a process known as Big Bang nucleosynthesis. This predominantly produced isotopes of hydrogen, helium, and small traces of lithium and beryllium, laying the groundwork for the elemental composition of the cosmos. If you're still around, subscribe to the channel if you haven't already. Let's keep going. Over the subsequent hundreds of thousands of years, the universe continued its expansion and cooling phase. During this time, photons, particles of light, constantly interacted with free electrons, creating a dense fog-like environment. About 380,000 years post-Big Bang, as the universe cooled to approximately 3,000 Kelvin, electrons began to combine with nuclei, forming the first neutral atoms in a process termed recombination. This event liberated photons, previously scattered by free electrons, giving birth to the cosmic microwave background radiation, now perceptible as a faint glow suffusing the cosmos. This time period, following the tumultuous aftermath of the Big Bang, laid the groundwork for the evolution of the intricate universe we observe today. From these initial moments emerged the primordial elements, shaping the universe's vast structures, galaxies, stars, and planets. Immediately after the Big Bang, the universe existed in a searingly hot, dense state, where energy levels were so extreme that particles and their antimatter counterparts were continuously created and annihilated. Among the first particles believed to exist in this era were quarks, leptons like electrons, their antimatter counterparts, and bosons, particles that mediate fundamental forces. During this period, known as the Quark Epoch, the universe was too hot and dense for quarks to bind into protons and neutrons. Instead, quarks and gluons, the bosons mediating the strong force, existed freely in what's termed a quark-gluon plasma. As the universe expanded and cooled, its energy decreased, allowing quarks to finally coalesce into protons and neutrons in a process called hadronization. Although electrons, a type of lepton, were present from the outset, the universe was too energetic for them to combine with protons to form atoms. This capability emerged later as the universe cooled further. In the early moments, neutrinos, another type of lepton, were also abundantly generated. Neutrinos interact minimally with other matter, and shortly after their formation, disengaged from other particles, streaming freely through space and forming a cosmic neutrino background akin to the cosmic microwave background radiation, but far trickier to detect. These initial particles, forged in the immediate aftermath of the Big Bang, served as the elemental building blocks for all the intricate structures observable in today's universe. Governed by the fundamental forces of nature, their interactions facilitated the evolution of the cosmos from a uniform sea of primordial particles into the diverse array of galaxies, stars, and planets we behold today. Early conditions of the universe. A mere fraction of a second post-Big Bang, the universe entered an exceedingly hot and dense phase termed the Planck era, paying homage to Max Planck, the progenitor of quantum theory. Spanning from 0 to roughly 10 to the negative 43rd seconds after the Big Bang, this epoch remains largely beyond the complete grasp of current physics. During this interval, the universe's temperature soared to such staggering heights that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into a singular fundamental force. The energy levels were so extraordinary that prevailing physical theories, like general relativity and quantum mechanics, fall short in accurately describing these conditions. Directly following the Planck era, the universe transitioned into the grand unification epoch, persisting until approximately 10 to the 36th second. Here, temperatures slightly cooled, facilitating the separation of the gravitational force from the other forces, marking the initial differentiation among the fundamental forces. This period may have also witnessed a phase of rapid inflation, during which the universe underwent exponential expansion within an infinitesimally brief span. According to inflation theory, the universe swelled in size by a factor of at least 10 to the 26th, ironing out any irregularities and setting the stage for a uniformly distributed and isotropic cosmos on expansive scales. Around 10 to the power of minus 32 seconds after the Big Bang, as the universe cooled and expanded, two fundamental forces, the strong nuclear force and the electro-weak force, a combination of electromagnetism and weak nuclear force, started to behave differently from each other. During this time, the universe existed as a plasma state, filled with a hot, dense mix of particles like quarks, leptons, such as electrons and neutrinos, along with their antiparticles, and various force-carrying particles like photons and gluons. The conditions were so intense that particles were constantly being created and destroyed. This brief moment after the Big Bang established the initial conditions for everything that followed in the universe. It determined the basic properties and arrangement of matter and energy, eventually leading to the formation of atoms, stars, galaxies, and the larger cosmic structures we see today. The incredible complexity and diversity of the cosmos can be traced back to this initial phase of rapid expansion and cooling. Cosmic inflation is a theory that aims to explain the very early stages of the universe's growth. It suggests that within the first tiny fraction of a second after the Big Bang, there was an extremely rapid and exponential expansion of the universe. According to this theory, the universe expanded by a factor of at least 10 to the power of 26 in less than 10 to the power of minus 32 seconds. This rapid expansion addressed several puzzling aspects of the Big Bang theory, such as the horizon problem, flatness problem, and magnetic monopole problem. It achieved this by making the observable universe uniform and isotropic, the same in all directions, and spatially flat to an extraordinary degree. Inflation is believed to have been driven by a hypothetical field called the inflaton field, which filled space. This field had properties that caused space itself to expand exponentially if it were in a particular high-energy state. As the inflaton field transitioned to a lower energy state, the rapid expansion slowed down, releasing the energy stored in the field through a process called reheating. This reheating filled the universe with the hot, dense plasma of particles typically associated with the traditional picture of the Big Bang. Evidence supporting cosmic inflation comes from studying the cosmic microwave background radiation, which shows slight temperature differences across the sky. These variations, known as anisotropies, are incredibly consistent in their distribution, matching what inflation theory predicts about how matter and energy were spread out in the early universe. Inflation theory suggests that these temperature differences should be nearly identical at all scales, a prediction that has been confirmed by detailed mapping of the cosmic microwave background by various space-based observatories. Cosmic inflation serves as a crucial link between the mystery of the universe's initial state and the later processes of Big Bang nucleosynthesis and structure formation. It's a cornerstone of our current understanding of cosmology, offering a compelling explanation for how a uniform, dense point could evolve into the vast, structured cosmos we observe today. During cosmic inflation, the early universe underwent rapid expansion, expanding exponentially within a fraction of a second after the Big Bang. This expansion stretched the universe from subatomic scales to macroscopic scales in an incredibly short time. This event had profound and lasting effects on the universe. One notable outcome is the universe's remarkable uniformity on large scales. Despite the presence of galaxy clusters and vast voids, the overall density of matter and energy, as well as the background temperature, remain consistent across vast distances. Cosmic inflation smoothed out any initial irregularities in the early universe's density, promoting a uniform distribution of matter and energy. This uniformity is evident in the consistent temperature of the cosmic microwave background radiation observed throughout the sky. Inflation theory also tackles the flatness problem, which notes that the universe appears spatially flat. According to the theory of general relativity, the universe's spatial curvature depends on its average density of matter and energy. Inflation stretched space so extensively that any initial curvature would now seem flat, similar to how the Earth's surface appears flat over short distances despite being spherical overall. During inflation, quantum fluctuations in the inflaton field were stretched to cosmic scales, seeding slight density variations. These variations later evolved under gravity's influence to form galaxies, stars, and other large-scale structures. These initial fluctuations left their mark on the cosmic microwave background, confirming inflation's predictions through meticulous mapping. Early universe conditions suggested the formation of exotic particles and space defects like magnetic monopolies, yet none have been observed, puzzling scientists. Inflation diluted the density of such exotic particles or defects to extremely low levels, explaining their rarity in the current universe. Cosmic inflation proposes a transformative phase that elegantly resolves these and other cosmic mysteries, establishing it as a cornerstone of modern cosmological theories. The rapid expansion, established initial conditions that allowed for the evolution of the dynamic and complex universe we see today. The Quark Epoch was a pivotal stage in the early universe following the Planck Epoch and lasting roughly from 10 to the power of minus 12 seconds to 10 to the power of minus 6 seconds after the Big Bang. During this period, the universe was brimming with an intensely hot and dense substance called quark-gluon plasma. Temperatures soared between about 10 to the power of 12 to 10 to the power of 15 Kelvin, so high that quarks, fundamental particles composing protons and neutrons, couldn't bind together. Instead, they existed freely alongside their companions, gluons, which are force carrier particles. This epoch was characterized by a universe too hot and dense for atomic nuclei or even atoms to form. Interactions mainly involved quarks, gluons, leptons like electrons and neutrinos, and their antiparticles constantly appearing and vanishing in pairs. During this phase, the four fundamental forces had already distinguished themselves. Gravity had separated from the others during the grand unification epoch preceding the Quark Epoch, while the strong, weak, and electromagnetic forces operated distinctly. As the universe expanded and cooled, energy density decreased until it reached a point where it could no longer prevent quarks from bonding. This shift signaled the end of the Quark Epoch and the start of the Hadron Epoch. In the Hadron Epoch, quarks combined to form protons and neutrons, collectively referred to as hadrons. This critical transition laid the groundwork for subsequent epochs of cosmic evolution, leading to the synthesis of basic atomic nuclei and the birth of neutral atoms, the fundamental building blocks of the chemical elements that populate the universe. During the initial phase of the universe, known as the Big Bang, there were significant and profound changes in temperature and density that form the basis of our current understanding of cosmology. Initially, immediately after the Big Bang, estimated to have occurred roughly 13.8 billion years ago, the universe was incredibly hot and dense, surpassing any conditions we can replicate on Earth. Temperatures soared to billions of degrees, allowing for the unification of the four fundamental forces of nature. As the universe expanded, a process ongoing today but at a much slower pace, it cooled down considerably. Within the first few minutes, the temperature decreased enough to enable the formation of simple atomic nuclei, a phase known as nucleosynthesis. This cooling and expansion continued over hundreds of thousands of years, eventually permitting electrons to join with nuclei, forming atoms, primarily hydrogen and helium. This transition marked the shift from a plasma state to a gaseous state. This stage laid the groundwork for the emergence of stars and galaxies, shaping the structure of the universe as we perceive it today. The intricate interplay between temperature and density during the universe's early stages underscores a remarkable period of transformation, crucial in shaping the cosmos we inhabit. The formation of subatomic particles, quarks, discovered in the 1960s through particle accelerator experiments, are the fundamental building blocks of matter in the universe. Unlike atoms, which were once considered the smallest units of matter, quarks are truly elementary particles with no underlying structure according to current scientific understanding. They are essential components of hadrons, such as protons and neutrons, which along with electrons form atoms. Quarks come in 6 varieties or flavors: up, down, charm, strange, top and bottom, each possessing distinct characteristics. For instance, a proton consists of 2 up quarks and 1 down quark, while a neutron contains 1 up quark and 2 down quarks. One of the intriguing aspects of quarks is the force that binds them together, the strong nuclear force mediated by particles called gluons. This force is so potent that it confines quarks within hadrons. They cannot exist independently, but are always found in combinations. This phenomenon, known as quark confinement, poses challenges for scientists in directly observing individual quarks, with their presence and properties inferred from high-energy experiments. The study of quarks not only enhances our comprehension of the universe's microscopic structure, but also sheds light on the early moments after the Big Bang, where these fundamental particles played a crucial role in matter formation. Through ongoing research in particle physics, scientists aim to delve deeper into the complexities of quarks, seeking to unveil more about the universe's fundamental essence and its origins. In the early universe, the emergence of quarks played a pivotal role shortly after the Big Bang during what's known as the Quark Epoch, occurring roughly 1/1,000,000th of a second, 10 to the power of -12 seconds, after the universe began to expand. This epoch was characterized by a hot, dense environment saturated with quarks, gluons, and other elementary particles, forming what scientists call a quark-gluon plasma. The universe's temperature at this stage soared to unimaginable heights, around 10 to the power of 12 Kelvin, allowing quarks and gluons to exist freely. As the universe expanded, it rapidly cooled, triggering significant changes in the state of matter. As temperatures dropped below a critical threshold, quarks began to bind together due to the strong nuclear force, the most influential force at these tiny distances. This force, mediated by gluons, effectively acted as glue, binding quarks together. Initially, quarks paired up or grouped into triplets, resulting in the formation of more complex particles like protons and neutrons, which consist of combinations of up and down quarks. This transition from free quarks to bound states within protons and neutrons marked the conclusion of the Quark Epoch and the onset of the Hadron Epoch, characterized by a universe primarily filled with protons and neutrons. This pivotal transition paved the way for the formation of atoms, stars, and ultimately galaxies in the evolving universe. The mechanisms governing the emergence and behavior of quarks in the early universe continue to be a focal point of intense investigation in particle physics and cosmology, offering valuable insights into the forces and conditions that shaped the cosmos. Antiquarks are the antimatter counterparts of quarks, the elemental constituents of matter in the universe. Like antimatter generally opposes matter particles, antiquarks mirror quarks in charge and other quantum attributes, but with precisely opposite values. This means each of the 6 quark flavors, up, down, charm, strange, top, and bottom, has a corresponding antiquark with identical mass but opposite electric and color charges, as well as other quantum characteristics. An intriguing aspect of antiquarks is their involvement in annihilation events. When a quark meets its corresponding antiquark, they can annihilate each other, releasing energy in the form of high-energy photons or other particles. This phenomenon underscores the universe's symmetry between matter and antimatter, yet curiously, the observable universe today appears predominantly matter-dominated. Antiquarks are not just theoretical entities, they have been generated and observed in high-energy particle collisions, such as those in particle accelerators. These experiments simulate the energetic conditions akin to those in the early universe, enabling physicists to scrutinize quark and antiquark properties and the strong force governing their interactions. Grasping the nature of antiquarks is vital for both theoretical and experimental particle physics, enriching our understanding of the fundamental principles dictating matter and antimatter. Their examination not only deepens our comprehension of the universe's minute building blocks, but also offers insights into the asymmetry between matter and antimatter, a central enigma in cosmology concerning the universe's prevailing matter dominance. Quarks and antiquarks engage in interactions through the strong nuclear force, one of the 4 fundamental forces of nature, mediated by particles called gluons. This force is distinguished by its remarkable strength, enabling it to bind quarks together, despite the repulsion between quarks of similar charges forming particles like protons, neutrons, and others. The exchange of gluons between quarks, whether they're matter or antimatter, follows a unique pattern described by the theory of quantum chromodynamics. Each quark possesses a property termed color charge, akin to electric charge in electromagnetism. However, instead of being positive or negative, color charge comes in 3 variations: red, green, and blue, along with their corresponding anticolors for antiquarks. Gluons, the carriers of the strong force, also carry combinations of color and anticolor charges, enabling them to serve as exchange particles between quarks and antiquarks. During this exchange, gluons can alter the color charge of involved particles while conserving overall color charge. A captivating aspect of quark-antiquark interaction is confinement. Unlike the electromagnetic force, which weakens as particles move apart, the strong force remains constant or even intensifies, effectively confining quarks and antiquarks within composite particles called hadrons, such as protons and neutrons. This explains why quarks and antiquarks are never found in isolation, but rather bound together within larger particles. Upon encountering an antiquark of corresponding anticolor, a quark can annihilate it, converting their combined mass into energy, often in the form of high-energy photons or other particle-antiparticle pairs. This interaction, while highlighting the annihilation potential between matter and antimatter, also illuminates the intricate array of forces and particles composing the universe's fundamental fabric. Through these interactions, quarks and antiquarks assume a pivotal role in shaping matter's structure and dynamics at the most elemental level. The strong nuclear force, one of the universe's 4 fundamental forces, played a decisive role in the early phases of particle formation post-Big Bang. It facilitated the cohesion of quarks into protons, neutrons, and other hadrons, governing their interactions to form atomic nuclei. During the universe's initial moments, characterized by extreme temperatures and densities, the strong force was instrumental in the transition from a quark-gluon plasma, a state where quarks and gluons existed freely, to a phase where quarks began coalescing into composite particles comprising observable matter. In the first microseconds post-Big Bang, as the universe cooled from its initially scorching temperatures, the strong force asserted itself, prompting quarks to merge into protons and neutrons, a process known as hadronization. This marked a crucial step in matter formation, as protons and neutrons serve as the foundational units of atomic nuclei. The strong force ensured their cohesion despite the kinetic energy that typically repels similarly charged particles. Subsequently, as the universe expanded and cooled further, protons and neutrons combined under the strong force's influence to generate the nuclei of basic elements like hydrogen, helium, and traces of lithium, a process termed nucleosynthesis. This epoch signified the universe's shift from a particle-rich environment dominated by individual quarks and gluons to one where matter began adopting a more recognizable form, laying the groundwork for the emergence of atoms, molecules, stars, and galaxies. The strong force, distinguished by its distinctive characteristics of confinement and asymptotic freedom, where it strengthens as quarks separate and weakens as they approach, was pivotal not only in binding quarks into composite particles, but also in orchestrating the formation of the early atomic nuclei. Devoid of the strong force, the universe would have persisted as a dispersed collection of unconnected quarks and leptons, devoid of the intricacy and organization we presently discern. By spearheading early particle formation, the strong force played a pivotal role in steering the universe's trajectory from its nascent stages post-Big Bang. What role do quantum fluctuations play? Quantum fluctuations stem from the bedrock of quantum mechanics, particularly Werner Heisenberg's uncertainty principle. This principle posits the impossibility of simultaneously determining a particle's exact position and momentum, implying that space's vacuum isn't devoid but pulsates with activity. Within this vacuum state, particles and antiparticles spontaneously materialize and annihilate in exceedingly brief intervals, giving rise to what are termed virtual particles. Understanding quantum fluctuations is pivotal for grasping the universe's fundamental fabric. Unlike the traditional notion of vacuum as utterly empty space, quantum mechanics unveils a lively and dynamic domain where particles like quarks and electrons, along with their antimatter counterparts, fleetingly emerge before swiftly annihilating. This phenomenon abides by the energy-time iteration of the uncertainty principle, permitting momentary energy conservation breaches that elude direct observation. Quantum fluctuations carry profound implications across physics, spanning cosmology to particle physics. They are believed to have wielded significant influence in the early universe, sowing the seeds for cosmic structure formation. Minute density variations in the universe's infancy, magnified over eons by gravitational forces, culminated in the intricate formations observed today, such as galaxies and galaxy clusters. Moreover, these fluctuations underpin the Casimir effect, wherein close proximity metal plates experience attraction due to the contrasting pressures exerted by quantum vacuum fluctuations inside and outside the gap between them. Quantum fluctuations highlight how the quantum world challenges our traditional understanding of reality. Even in seemingly empty spaces, the fabric of reality behaves dynamically, defying classical expectations. These fluctuations played a pivotal role in shaping the universe during its early stages, particularly during cosmic inflation, a rapid expansion believed to have occurred right after the Big Bang. During inflation, these tiny subatomic fluctuations were stretched across vast scales as the universe expanded. Slightly denser regions, influenced by these fluctuations, began attracting more matter due to gravity. Over time, this process amplified these initial irregularities into the sprawling cosmic web of galaxies and clusters we see today. According to the inflationary model, these quantum fluctuations serve as the seeds for temperature variations in the cosmic microwave background, CMB, radiation. The CMB provides a snapshot of the universe around 380,000 years after the Big Bang. Observations from satellites like COBE, WMAP, and Planck have confirmed tiny temperature fluctuations in line with quantum theory and inflation predictions. These fluctuations indicate regions of varying densities, supporting the notion that quantum fluctuations laid the groundwork for cosmic structure formation. Furthermore, the influence of quantum fluctuations during inflation suggests that the universe's properties on its largest scales are influenced by events at the quantum level, bridging the gap between quantum mechanics and general relativity. This interaction between the smallest and largest scales showcases how quantum fluctuations in the universe's early moments have significantly impacted its structure and evolution, affecting the distribution of galaxies and shaping the cosmos as we know it. Quantum fluctuations can spark the creation of particles, a captivating occurrence rooted in quantum field theory. In this framework, even what we perceive as empty space isn't devoid of activity. It's filled with fluctuating fields representing different particle types. These fluctuations can fleetingly generate pairs of particles and their antimatter counterparts from seemingly nothing, thanks to the Heisenberg uncertainty principle. This principle allows for the brief appearance of energy in particle form, provided it vanishes swiftly enough not to disrupt energy conservation laws over observable timeframes. This process illustrates the concept of virtual particles, particle-antiparticle pairs that spontaneously come into being and promptly annihilate each other. While these particles can't be directly observed due to their fleeting nature, their indirect effects leave a tangible mark and have significant physical implications. A prime example is Hawking radiation surrounding black holes. According to Stephen Hawking's groundbreaking theory, quantum fluctuations near a black hole's event horizon can cause one particle of the pair to be trapped by the black hole, while the other escapes as radiation, leading to the black hole losing mass over time. Similarly, the Casimir effect demonstrates how quantum fluctuations can generate a measurable force between two uncharged parallel plates placed very close together in a vacuum. The fluctuating energy density of virtual particles between the plates and outside them creates a pressure that pushes the plates together. This phenomenon arises from the constraints on the wavelengths of virtual particles that can exist between the plates compared to those outside, altering the vacuum's energy in these regions. Quantum fluctuations aren't just about particle creation, they reveal the ever-changing nature of the quantum vacuum and highlight the deep connections between the forces governing the universe at both tiny and cosmic scales. These fluctuations indirectly shape the formation of protons, linking the fundamental principles of quantum mechanics with the intricate structures of particle physics' standard model. The tale of proton formation, influenced by quantum fluctuations, begins in the early universe, specifically during the Quark Epoch, shortly after the Big Bang. At this time, the universe was dense and energetic enough for quarks, gluons, and their antiparticles to freely emerge from the available energy, courtesy of quantum fluctuations. These fluctuations, shifts in energy levels within quantum fields, momentarily produced pairs of particles and antiparticles. In the intense heat of this epoch, it led to a bustling mix of quarks, antiquarks, and gluons, constantly materializing and disappearing. As the universe expanded and cooled, it reached a point where it could no longer sustain these fluctuations in a manner allowing quarks and antiquarks to exist freely. The surviving quarks started to merge, forming stable combinations under the influence of the strong force. This force, governed by quantum chromodynamics, feeds on the energy from these fluctuations, using it to bind quarks into protons and neutrons. This quantum aspect emphasizes the counterintuitive notion that even the vacuum of space is teeming with potential energy capable of affecting matter formation. The protons formed during this early period have remained steadfast over billions of years, eventually becoming integral parts of the atomic nuclei constituting the universe's chemical elements. The subtle impact of quantum fluctuations on this process underscores the close relationship between quantum mechanics and particle physics, demonstrating how the rules governing the universe's tiniest scales influence the structure and endurance of matter across vast cosmic timeframes. The cooling of the universe is intricately linked to its expansion, a phenomenon that commenced with the Big Bang roughly 13.8 billion years ago. According to cosmological models, the universe's initial state was an incredibly hot, dense point. As it expanded, the space between its constituent particles also expanded, causing the energy density and temperature to decline gradually. This cooling process can be likened somewhat to how gases behave in thermodynamics. When a gas expands, it performs work against its surroundings and loses energy, resulting in a drop in temperature. Similarly, as the universe expanded, the wavelengths of the radiation filling it stretched out. This wavelength stretching corresponds to a shift towards the red end of the electromagnetic spectrum, indicating a decrease in energy or cooling. In the earliest moments following the Big Bang, the universe was so hot that matter and antimatter particles were continuously being created and annihilated in pairs. However, as the universe expanded and cooled, it eventually reached a temperature where these high-energy processes became untenable. This led to a prevalence of matter over antimatter and the formation of stable particles like protons and electrons. This cooling phase also facilitated the genesis of the first atomic nuclei through a process known as nucleosynthesis, occurring roughly 3 minutes after the Big Bang. At this point, the universe had cooled sufficiently for protons and neutrons to combine into nuclei without being ripped apart. Hundreds of thousands of years after the Big Bang, as the universe continued to expand and cool, it entered a crucial phase known as the recombination epoch. During this period, electrons could finally bind with nuclei, forming neutral atoms. This marked a significant milestone in the universe's evolution. The cooling of the universe has been a pivotal process, profoundly influencing the cosmos we inhabit today. It has not only facilitated the formation of fundamental particles and structures, but has also paved the way for the emergence of life. This cooling process, intimately tied to the universe's expansion, has dictated the sequence of key cosmological events that have shaped the universe's present state. Initially, the extreme temperatures of the early universe prevented the formation of stable matter as we recognize it. Instead, particles of matter and antimatter continuously formed and annihilated in a highly energetic environment. However, as the universe expanded and cooled, these intense processes gradually subsided. This allowed matter to dominate over antimatter, leading to the creation of stable particles such as protons and neutrons. As the universe continued to cool, it entered the epoch of nucleosynthesis. During this brief period, conditions were ripe for protons and neutrons to combine, forming the nuclei of the lightest elements like hydrogen, helium, lithium, and beryllium. This process laid the groundwork for the rich diversity of chemical elements observed in the universe today. Moreover, the cooling of the universe heralded the recombination epoch, a pivotal moment when electrons could finally join with nuclei to form neutral atoms. This transformation drastically reduced the scattering of photons by free electrons, allowing light to travel freely through space for the first time. The release of photons during this period formed what we now call the cosmic microwave background radiation, offering us a glimpse into the universe's early stages and serving as compelling evidence for the Big Bang model. On a grander scale, the cooling of the universe laid the groundwork for gravitational forces to gather matter, ultimately giving rise to the first stars and galaxies. These cosmic structures further synthesized heavier elements within their cores, contributing to the chemical diversity necessary for planets and, eventually, life to emerge. In essence, the significance of the universe's cooling stretches from enabling the formation of the first stable particles to fostering the emergence of intricate structures and life itself. It embodies a profound narrative of transformation and complexity emerging from simplicity, guided by the laws of physics and the initial conditions of the cosmos. The cooling of the universe profoundly impacted particle interactions, fundamentally shaping the transition from a primordial soup of elementary particles to the structured matter composing the cosmos today. In the blisteringly hot and dense conditions immediately after the Big Bang, particles possessed too much energy to bind together, resulting in a state where matter existed as a plasma of quarks and leptons in constant flux. As the universe expanded and cooled, the average energy of particles decreased. This cooling brought about several pivotal effects on particle interactions. When the universe cooled to below a certain critical temperature, the strong nuclear force could finally overcome the kinetic energy of quarks, allowing them to bind together and form nucleons, protons and neutrons. This marked the conclusion of the Quark Epoch and the dawn of the Hadron Epoch, signifying a significant shift in the organization of matter. As the universe continued to cool, it paved the way for nucleosynthesis, the process responsible for the formation of the first atomic nuclei. This remarkable phenomenon occurred a few minutes after the Big Bang, when the temperature dropped sufficiently for protons and neutrons to merge into the nuclei of the lightest elements without being ripped apart by high-energy photons. This epoch primarily yielded hydrogen, helium, and small amounts of lithium and beryllium. Several 100,000 years post-Big Bang, the universe had cooled to a point where electrons could combine with atomic nuclei, forming neutral atoms. This recombination phase had a profound impact on particle interactions by greatly reducing photon scattering. Consequently, the universe became transparent to radiation, allowing light to traverse space freely. The photons liberated during this period composed the cosmic microwave background radiation, offering a critical window into the universe's infancy. Moreover, the cooling of the universe facilitated the gravitational collapse of matter. Denser regions attracted more particles via gravitational forces, culminating in the birth of stars and galaxies. Within these stellar cores, nuclear fusion processes commenced, synthesizing heavier elements from lighter ones and enriching the cosmic chemical inventory. At each stage of cooling, the kinetic energy of particles diminished, facilitating novel interactions driven by various fundamental forces, particularly the strong and electromagnetic forces. This gradual evolution shaped the universe's trajectory, transitioning from a homogeneous hot plasma to a richly structured cosmos teeming with diverse celestial bodies and eventually giving rise to life as we comprehend it. Certainly, quarks, the building blocks of matter, began to coalesce into composite particles such as protons and neutrons, collectively known as nucleons, during a phase termed the Hadron Epoch. This epoch spanned from approximately 1 microsecond to 1 second after the Big Bang, a time when the universe had cooled sufficiently from its initial blistering temperatures. In the immediate aftermath of the Big Bang, the universe was so intensely hot and dense that quarks couldn't bind together due to the overpowering kinetic energy keeping them apart. This state, termed the quark-gluon plasma, resembled a dense soup-like mixture where quarks, antiquarks, and gluons roamed freely. However, as the universe expanded, it gradually cooled, diminishing the average kinetic energy of these constituent particles. When the temperature dropped to around 10 to the power of 12 Kelvin, the strong nuclear force, responsible for binding quarks together, triumphed over the kinetic energy separating them. This force, mediated by particles called gluons, initiated the process of amalgamating quarks into larger particles known as hadrons. Specifically, combinations of up and down quarks gave rise to protons, comprising 2 up quarks and 1 down quark, and neutrons, comprising 1 up quark and 2 down quarks. This transition from quarks and gluons freely flowing in the quark-gluon plasma to the formation of composite particles marked a pivotal shift in the universe's matter composition. The Hadron Epoch represents a crucial phase in the early universe, setting the stage for subsequent processes like nucleosynthesis, which facilitated the genesis of the first atomic nuclei, eventually leading to the formation of atoms, stars, and galaxies. Let's explore the basics of hadrons, the fundamental particles that make up the nucleus of atoms. Hadrons are essentially clusters of even smaller particles called quarks, held together by a powerful force known as the strong nuclear force, which operates through intermediary particles called gluons. There are two main types of hadrons, baryons and mesons. Baryons, like protons and neutrons, consist of 3 quarks each. For example, a proton has 2 up quarks and 1 down quark, while a neutron has 1 up quark and 2 down quarks. Mesons, on the other hand, are made of 1 quark and 1 antiquark pair. These particles play a crucial role in maintaining the stability of atomic nuclei. The strong force is incredibly effective at holding quarks together within a single hadron, a phenomenon known as quark confinement. This force not only keeps quarks bound within hadrons, but also acts between hadrons, preventing the atomic nucleus from falling apart, despite the electromagnetic repulsion between positively charged protons. Studying hadrons is vital in the field of particle physics, as it helps us understand the strong nuclear force and how matter behaves under extreme conditions, such as those encountered in neutron stars or during the universe's early moments after the Big Bang. Experiments conducted in large particle accelerators like the Large Hadron Collider, LHC, involve colliding hadrons at high speeds to delve deeper into the fundamental nature of matter and the forces that shape the universe. Hadrons, the building blocks of matter, come in 2 main types, baryons and mesons. Baryons, like protons and neutrons, consist of 3 quarks each, while mesons are formed from a quark and an antiquark pair. The arrangement of quarks within hadrons follows specific rules outlined by quantum chromodynamics, a theory governing the strong force interactions among quarks and gluons. Baryons and mesons, though both part of the hadron family, have distinct characteristics. Baryons, with their 3-quark makeup, exhibit a half-integer spin, falling into the category of fermions. This classification means they adhere to the Pauli exclusion principle, preventing identical fermions from occupying the same quantum state simultaneously. On the other hand, mesons, comprised of a quark and an antiquark pair, possess an integer spin, making them bosons. Unlike fermions, bosons can occupy the same quantum state in large numbers without constraint by the Pauli exclusion principle. These differences in quantum nature translate into diverse roles in the universe. Baryons, being the majority mass carriers of visible matter, form the basis of stars, planets, and living organisms. Mesons, however, often serve as mediators of the strong nuclear force, facilitating interactions between particles like protons and neutrons within atomic nuclei. Observing these particles typically requires high-energy environments like particle accelerators or cosmic ray interactions in the Earth's atmosphere. The formation of stable particles like protons, which are essential constituents of the universe, stems from the principles of quantum chromodynamics. For instance, protons, a type of baryon, are composed of 2 up quarks and 1 down quark, giving them their characteristic positive electric charge. The journey of proton formation begins at the minuscule scale of the quantum foam, where the strong nuclear force reigns supreme among the 4 fundamental forces. This force, facilitated by gluons, acts as a binding agent between quarks, effectively keeping them together within a proton. Despite the electromagnetic force's attempts to push positively charged quarks apart, the strong nuclear force prevails within the compact space of a proton, ensuring its stability. The intricate interaction between quarks and gluons, guided by the laws of quantum mechanics, orchestrates the formation of protons. Once formed, protons exhibit extraordinary stability, enduring for time spans surpassing the age of the universe. They serve as essential components of atomic nuclei, forming the backbone of matter in the universe, from the simplest hydrogen atom to the heaviest elements. Neutrons, akin to protons in being baryons composed of quarks, follow a similar but slightly different arrangement. Comprising 1 up quark and 2 down quarks, neutrons possess unique properties, notably their electrically neutral nature. The formation of neutrons involves the interplay of fundamental forces, primarily the strong nuclear force mediated by gluons. Gluons play a crucial role in holding quarks together within neutrons, counteracting the repulsive forces that would otherwise tear them apart. The balance of up and down quarks within. Neutrons determines their mass and stability, rendering them slightly more massive yet less stable than protons in isolation. Neutrons are formed in various astrophysical phenomena, such as supernova explosions, where extreme pressure and energy conditions enable the conversion of electrons and protons into neutrons, accompanied by the release of neutrinos. Furthermore, within the nucleus of an atom, protons can convert into neutrons and vice versa through beta decay, a phenomenon governed by the weak nuclear force. This mutual transformation of protons and neutrons, orchestrated by subtle forces, is foundational to the intricate structure of matter and the vast array of elements in existence. The interaction and interchangeability of these particles are pivotal in shaping the universe's fabric, influencing the diversity of matter and the life cycle of stars. At the core of every atom lies a nucleus formed by the binding of protons and neutrons, a process steered by the strong nuclear force. This foundational fusion lays the groundwork for the periodic table, dictating each element's identity and isotopic variations based on the nucleus's proton-neutron composition. Within the blazing cores of stars, this balance of protons and neutrons undergoes dynamic shifts, fueling nuclear fusion reactions that sustain stellar energy and generate heavier elements essential for life and planetary formation. For instance, hydrogen nuclei, protons, fuse to form helium, releasing vast amounts of energy and illuminating the cosmos. As stars evolve, more intricate fusion processes ensue, generating and consuming neutrons while transmuting elements up the periodic table. This cosmic alchemy culminates in the synthesis of heavy elements ubiquitous in our world, from the calcium in our bones to the iron in our blood. Furthermore, the decay of neutrons into protons and vice versa through various forms of beta decay significantly influences the universe's element stability and abundance. This decay mechanism also plays a vital role in shaping celestial bodies' thermal evolution and the interstellar environment. The intricate interplay between protons and neutrons weaves a tapestry of complexity, determining not only the atomic blueprint of matter, but also energizing the celestial mechanisms that illuminate the cosmos and forge the diverse elements comprising our universe and beyond. Their perpetual dance underscores the delicate equilibrium of forces and particles shaping our cosmic comprehension. Our early universe, nuclear fusion. Nuclear fusion stands as a potent force within the heart of stars, including our Sun, serving as the primary engine powering the universe. This awe-inspiring process involves the melding of lighter atomic nuclei, like hydrogen, into heavier ones, such as helium. Unlike nuclear fission, where heavy nuclei split into lighter ones, fusion harnesses the nuclei's mass to yield an immense amount of energy, exceeding the capability of any chemical reaction. This phenomenon, encapsulated in Einstein's iconic equation mc2, underscores the conversion of mass into energy. Fusion unfolds under extreme temperatures and pressures, stripping electrons away and birthing a plasma, an energetic state replete with free charged particles. Here, the repulsion between positively charged nuclei is counteracted by the strong nuclear force as they approach closely, facilitating fusion. This process not only fuels stellar cores, but also drives the synthesis of elements beyond hydrogen through diverse fusion reactions. In stars like our Sun, hydrogen nuclei merge into helium via the proton-proton chain reaction. More massive stars engage in elaborate fusion cycles, such as the carbon-nitrogen-oxygen process, contributing to the cosmic array of elements. The quest for controlled fusion on Earth seeks to mimic this stellar phenomenon, offering a promising avenue for abundant, clean energy. Despite the formidable technical hurdles, successful fusion replication could revolutionize global energy production, offering a sustainable alternative. During the universe's infancy in the Big Bang nucleosynthesis era, occurring roughly 3 to 20 minutes post-Big Bang, fusion played a pivotal role in shaping elemental composition. As the universe cooled from its primordial state of extreme heat and density, quarks fused into protons and neutrons, though electrons remained unbound, creating a plasma teeming with charged particles. As the universe cooled and expanded, it reached a crucial point where nuclear fusion became possible. The initial fusion process involved protons and neutrons combining to form deuterium, a heavier form of hydrogen releasing a modest amount of energy. Deuterium then acted as a building block, fusing with additional protons and neutrons to generate helium-3 and tritium, hydrogen-3, which could further merge to produce helium-4, the most stable and prevalent helium isotope. This period of nuclear fusion, known as Big Bang nucleosynthesis, was fleeting due to the rapid changes in the universe's conditions. Despite its brevity, the majority of the universe's helium was synthesized during this time, along with small quantities of other light elements like deuterium, lithium, and beryllium. The precise proportions of these early elements, as predicted by Big Bang nucleosynthesis theories, align remarkably well with astronomical observations, offering robust validation for the Big Bang model. Unlike the gradual fusion processes in stars spanning billions of years, Big Bang nucleosynthesis was a singular event that unfolded in a rapidly evolving cosmic landscape, setting the stage for the universe's chemical evolution. During the early moments post-Big Bang, protons played a pivotal role in initiating nuclear fusion, laying the groundwork for the universe's elemental composition. As relics of the primordial universe's cooling phase, protons constituting hydrogen nuclei were abundant and primed to participate in the creation process. In the intense conditions of Big Bang nucleosynthesis, nuclear fusion occurred momentarily, with protons initiating the initial fusion reactions leading to helium formation, the universe's second most prevalent element. The nuclear fusion process in the early universe significantly influenced its elemental makeup. Initially, protons and neutrons merged to form deuterium, a heavy hydrogen isotope accompanied by the release of energy in the form of photons. Despite the simplicity of this reaction, the formation of deuterium faced challenges due to the high temperatures prevailing at that time. These elevated temperatures often disrupted deuterium nuclei before they could engage in further fusion reactions. However, as the universe expanded and cooled, the photon energy decreased, enabling subsequent fusion reactions to proceed unhindered. Deuterium acted as a crucial intermediary in the progression of fusion reactions. By merging with protons, it facilitated the gradual buildup of helium, enriching the elemental inventory of the cosmos through successive reactions. This transformative era placed protons at the nucleus of cosmic transmutation, catalyzing the genesis of novel nuclei and decisively shaping the elemental blueprint of the infant universe. Protons played a foundational role in the infancy of nuclear fusion, marking the dawn of the universe's evolution from a primordial particle broth to a cosmos teeming with a diverse assortment of elements. Their ubiquitous presence, coupled with the straightforward fusion dynamics of hydrogen, set the groundwork for the intricate chemical ballet that would eventually spawn stars, galaxies, and life itself. The emergence of the first elements via nuclear fusion stands as a monumental episode in cosmic chronicles, unfolding shortly after the cataclysmic Big Bang birthed the universe into existence. As the cosmos swiftly expanded, it cooled from its initial fiery state, providing the backdrop for the inaugural acts of nucleosynthesis. This process commenced with the elemental building block of hydrogen, which predominated in the primordial cosmic brew. Under the extreme conditions of early cosmic epochs, protons, the core of hydrogen atoms, joined forces with neutrons, forging the inaugural complex nucleus, deuterium or heavy hydrogen, comprising one proton and one neutron. The genesis of deuterium marked a pivotal juncture, acting as a gateway to further fusion processes. Progressing from deuterium, the journey towards generating helium-4, the subsequent stable nucleus, unfolded through a series of stages. Deuterium nuclei could merge, with protons yielding helium-3, comprising two protons and one neutron. Subsequently, collisions between helium-3 nuclei could trigger the synthesis of helium-4, liberating two protons to engage in subsequent reactions. This succession of fusion cascades didn't halt with helium, albeit in lesser quantities. Interactions involving helium alongside other light nuclei like deuterium and helium-3 engendered minute quantities of lithium and beryllium. However, the formation of these heavier nuclei encountered greater obstacles due to the escalating energy requirements of reactions and the scarcity of suitable reactants. These initial fusion episodes, unfolding within the universe's nascent minutes, imparted a foundational blend of elements, primarily hydrogen and helium, interspersed with traces of lithium, beryllium, and potentially boron. This elemental mosaic set the groundwork for the subsequent emergence of stars, galaxies, and the intricate chemical milieu essential for life's evolution. The precise proportions of these primordial constituents, shaped by the environmental conditions and governing laws of early cosmic epochs, persist as discernible signatures in the ancient structures of the cosmos, offering glimpses into the universe's formative epochs. Hydrogen. Formation. Hydrogen holds the title of the most common element in the universe, thanks to its straightforward nature and the circumstances prevailing during the universe's inception. It originated shortly after the Big Bang and stands as the simplest element, comprising only one proton and an electron. This simplicity meant that it was the first element to materialize as the universe cooled from its initial intensely hot and dense state. During the explosive expansion of the Big Bang, the cosmos was a swirling mix of energy. As it expanded and cooled down, basic particles began to merge into protons and neutrons. The gradual cooling allowed these protons and neutrons to form the simplest atomic nuclei, with hydrogen being the foremost. The vast number of protons generated and the ease of capturing an electron to create a neutral atom meant that hydrogen swiftly became the primary building block of the early universe. Furthermore, the circumstances conducive to creating heavier elements during the Big Bang nucleosynthesis were fleeting. This process favored the formation of hydrogen and helium, with helium being the next simplest nucleus, consisting of 2 protons and usually 2 neutrons. Although a small amount of lithium was also produced, the early universe lacked the requisite conditions, such as the extreme pressures and temperatures found in stars, to facilitate the creation of heavier elements through nuclear fusion at this early stage. This initial production laid the groundwork for hydrogen's dominance. Stars play a pivotal role in solidifying hydrogen's widespread presence through their life cycles. Essentially, stars act as colossal nuclear fusion reactors, initially fusing hydrogen atoms into helium and eventually into heavier elements during their later stages. Since stars commence their lives by fusing hydrogen and require vast amounts of hydrogen to sustain themselves over millions to billions of years, hydrogen maintains its status as the predominant element in the universe. Thus, the straightforward nature of hydrogen, coupled with the universe's conditions at its inception and the ongoing processes within stars, ensures that hydrogen not only emerged as the primary element in the universe, but also continues to dominate. The emergence of hydrogen as the universe's most abundant and simplest element played a fundamental role in shaping cosmic evolution. Following the Big Bang, the universe predominantly consisted of vast expanses of hydrogen gas interspersed with helium and trace amounts of lithium. This primal composition laid the groundwork for all subsequent cosmic developments. Hydrogen's impact on the universe's evolution is profound and diverse. Initially, it served as the building blocks for the earliest stars. Gravitational forces pulled together clouds of hydrogen gas, compressing them until the pressures and temperatures in their cores ignited nuclear fusion. These first-generation stars, known as population 3 stars, converted hydrogen into helium and later in their life cycle into heavier elements. This transformative process not only illuminated the universe, ending the cosmic dark ages, but also seeded the cosmos with the materials necessary for the formation of future stars, planets, and later on, life. The arrangement of hydrogen gas played a crucial role in shaping the overall structure of the universe on a large scale. Regions with slightly higher density in the nearly uniform early universe attracted more gas due to gravity, triggering the formation of galaxies. Within these fledgling galaxies, vast hydrogen clouds acted as breeding grounds for subsequent generations of stars. Additionally, the simplicity and abundance of hydrogen serve as vital signposts in comprehending the universe's evolution. The absorption and emission spectra of hydrogen offer astronomers valuable tools for measuring the universe's expansion, determining the age of galaxies, and investigating the formation of stars and planetary systems. Hydrogen holds a central position in sustaining life as we know it. Not only is it a fundamental building block of water, but the fusion of hydrogen into helium powers the sun, providing the crucial energy necessary for life on Earth. Moreover, the transformation of hydrogen atoms into heavier elements within stars has enriched the chemical diversity required for the intricate molecules that form living organisms. Essentially, the genesis of hydrogen laid the groundwork for the complexity and splendor observed in the cosmos today. Its presence fueled the stars illuminating the universe, contributed to the formation of galaxies, and facilitated the genesis of the chemical elements comprising the world around us, underscoring the pivotal role of hydrogen in the grand cosmic saga. As the simplest and most abundant element in the universe, hydrogen has played an indispensable role in steering the universe's narrative from its inception to its current state. Its significance spans various crucial facets of cosmic development, from the birth of the first stars to the formation of life-supporting planets. Initially, hydrogen served as the primary fuel for the universe's earliest luminaries. The gravitational aggregation and compression of primordial hydrogen clouds paved the way for the emergence of the earliest stars. These stellar entities initiated the process of nuclear fusion, converting hydrogen into helium and unleashing energy that illuminated the universe. This transformative epoch marked a transition from the cosmic dark ages to an illuminated universe teeming with stars. Moreover, the fusion reactions occurring within stars, starting with hydrogen, represent the universe's method of creating heavier elements, which form the foundation of planets, asteroids, and all known life forms. As stars mature and deplete their hydrogen reservoirs, they transition to fusing helium into progressively heavier elements, ultimately dispersing these elements into space upon their demise in supernova explosions. This cosmic recycling and dispersal of materials have contributed to the intricate, chemically diverse universe we observe today, facilitating the formation of terrestrial planets and complex organic compounds. Hydrogen also serves as a crucial tool in astronomy. Its presence and behavior in interstellar space aid scientists in mapping the universe, delineating the spiral arms of galaxies, and understanding the broader structure of cosmic matter. The distinctive spectral lines of hydrogen enable astronomers to gauge the redshift of distant galaxies, offering evidence for the universe's expansion and assisting in determining distances on cosmic scales. Additionally, the abundance of hydrogen in nebulae and protoplanetary disks around young stars plays a pivotal role in the formation of planetary systems. Hydrogen compounds such as water are indispensable for fostering habitable environments on planets like Earth. Consequently, the widespread presence of hydrogen in the universe has been a prerequisite for the emergence of life as we know it. In essence, hydrogen transcends being merely a constituent of the universe. It actively shapes its evolution. From igniting the first stars to being indispensable for life, hydrogen's influence in the cosmos is profound, underscoring its significance in the grand narrative of the universe's evolution. We love to explore scientific mysteries on this channel, but don't worry, because there are easy and free ways to ponder on these topics, like with Brilliant, who is sponsoring this video. Brilliant provides specialized courses that can help you explore complex scientific questions, whilst also building a powerful daily learning habit. If you're interested in problem solving, critical thinking, logical thinking, and more, Brilliant is the place for you. Their courses are designed to teach you how to think and solve problems through engaging, interactive lessons. What I personally like about Brilliant is that it caters to learners of all ages, all the way from beginners to professionals, and offers a variety of content in math, data analysis, programming, and AI. I genuinely appreciate how Brilliant's lessons emphasize scientific thinking. Their comprehensive, interactive approach offers a deeper understanding, allowing me to grasp scientific principles more effectively than ever. In the scientific thinking course, you'll have the chance to apply these principles, solve fascinating puzzles, and make informed predictions about the world, uncovering the science behind everyday phenomena. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/SpaceDrift or click on the link in the description. You'll also get 20% off an annual premium subscription.